Welcome to Spring LIB.
All right, so a problem gives us some initial equations here to work with that describe the path of a particle moving through some sort of space. So we have an equation here that describes the motion in the x direction, which this may actually look very familiar if I were to write x equals x initial plus the v x initial times t plus 1/2 a x times t squared. That's this equation. What has been done is there's been stuff added to it and some stuff taken out, and even a zero left in here. So we'll analyze that in a second. This bottom equation is the same thing, just in the y world. So it's y equals y sub I plus v sub y times I times t plus 1/2 a sub y. Same equation, just it's looking at the y direction. So that's what both of these equations are doing here. So the first thing that we need to figure out here is the athlete's position, right? So we want to be able to figure out some sort of position initially, like a coordinate pair that describes where the particle or the object starts, right? So the way we can do this is pretty straightforward. So remember, this is our equation here that we're kind of comparing the top ones to. Look at the x. Let's start with the x. There's a zero right here. The place where the zero is where this x initial would normally be. So what does that tell us? That tells us that this x initial right here is going to be 0. What about the y? So let's go ahead, go to our formula. I know it says x, but it's the same thing, just with the if you were to put y here versus the x. But we still look at what is in the same spot here, the initial position spot. And look at that, 0.840 meters. So we'll go ahead and we'll put that right here, 0.84. Cool. And there you go. That's your initial position written as some sort of coordinate pair that describes the motion. If you wanted to write it a little bit differently, you could say x initial equals 0, while y initial equals 0.84. Okay, so how about we try to find the initial velocity? It's a little bit trickier, but again, what we have to do is take a look at the vectors and break them down. So we have, let's label this part B here. We have some velocity in the x direction initially. And the way we describe that normally is by the v initial vector multiplied by the cosine of the angle that we are analyzing here. That's normally what we do. So we'll do the similar thing here. This is going to be equal to 11.2. We take that initial velocity. Look, that's where the initial velocity would normally be. So we'll do 11.2 times cosine of, there's the angle, 18.5. These guys are actually stuck together, technically speaking, in this problem. They come as a pack for the x dimension, because they're describing the velocity component, which is, or the velocity vector, which is 11.2, and they're describing it in the x direction, which you have to multiply by the trig function to describe that. So that gives you the velocity in the x direction initially, and by using the same technique for the y, we can even save some time here. We know it's going to be vi, sine of the angle. So we'll go ahead and just do that right here. 11.2 sine of 18.5. Cool. There's your two velocity components, which is nice to have. But we do want to write that in unit vector notation. That's the big thing here. So how are we going to do that? Well, we actually have to compute these. So let's take this a step forward real quick, just to be official here. And let's get the proper unit vector notations for this guy. So we have 10.6 meters per second. If you run through that math, this guy, if you run through 11.2 times sine of 18.5, 3.55. Cool. Box those in here. All right. Now we're going to move on to part C, which I'll sneak in down here, which is we want to figure out the time to get to the final position from the initial position. So we're going to go ahead and use this equation to start. And this will quickly turn into a quadratic, as you guys will see. Moving along here, we can go ahead and plug in what we know. 0.36 is the final position for the y. So for this one, there's the final position sitting right there. So we'll put this in first, 0.36. The y initial position is 0.84. So we'll put that in here, filling it in. Just comparing the equations, guys. That's what this is. This whole problem has really been about. 0.84, and then plus the velocity vector in the y direction initially, which is 3.55 t, plus the last part, which is the 1/2 minus g t squared. We're going to move this guy over here. So we want to do some reorganizing of our equation here. So we're going to do just very slight reorganizing so it makes sense. So it actually looks like a quadratic. 9.81 divided by 2 is 4.92 t squared. And I'm going to move that to the other side. So we lose the negative. And I'm going to move the 3.55 over. So that gets a negative 3.55 t. And then, of course, we have the 3.6 minus the 0.84. And when you do that, you're going to get negative 0.48. This is equal to 0. At this point, you're going to go ahead and use the quadratic formula, which I'll write here. And then I'm going to just write the solutions to this one because quadratic formula is much more of a mathematical technique than a physics technique. So we will leave it at that. And a lot of calculators these days have built-in functions to solve this, or it's just already sometimes well known in someone who's taken a physics class already. Of course, you just go through A, B, and C, and go ahead once you plug in all the stuff that you know. For this is going to break down into two equations here, or two solutions, and you have a negative 0.116, and you have a positive 0.841. 841 seconds. So they present you with two solutions, which is typically what happens when you solve a quadratic, because you're finding roots in a quadratic, and a quadratic typically intersects the x-axis twice. In fact, well, imagine it would always. But anyway, besides the fact, we're going to want to pick the positive solution here, because this is a time solution, so you do want to get the positive one, because you're not going to have a negative time in these instances here. So negative 8.41, and this down here is a seconds. I want to make sure I'm very clear. It's a seconds, not a G. Look at G for a second. There we go, seconds. All right. So let's go ahead. We have our time, which is powerful, and now we can go ahead and find that final, that x final that we've been looking for since the beginning. We can go ahead and just take this formula right here, and we'll bring it down. And we just got to plug in what we know for t, which we just found out some good information here. So we'll go ahead and do that now. I'm going to do it down here. X final equals, we can just ignore the 0. There's no need because it's just 0. So we'll go right into the 11.2 times cosine, 11.2 times cosine of 18.5, which, if I can remind you guys, we've already done that. It's right here, 10.6. 10.6 times the 8.41. And when you do that, we're looking at a final answer of 8.93 meters. Excellent.